The machine learning industry operates on a specific framework for alignment, reinforcement learning from human feedback, or RLHF. This approach treats artificial intelligence safety as a behavioral training problem. The limitation of RLHF is in its target. Behavioral training attempts to modify model outputs through probabilistic rewards, rather than architecturally constraining the reasoning process itself. To guarantee safety, we have to look past behavioral nudges and build structural, governance-first infrastructure that enforces strict reasoning boundaries. We can observe this through Helix Project AI, a framework built entirely around trust by design and verifiable memory principles. This infrastructure is driven by the principles of shape theory. In this model, you can allow a model to generate an unconstrained cloud of probabilistic text or force its output through rigid brackets of deterministic enforcement. Shape theory posits that intelligence and reasoning quality are consequences of structural integrity. Structure is never neutral. If we require reliable artificial intelligence, alignment must transition from being a probabilistic behavioral suggestion to a mechanical architectural problem. In a language model context, unstructured casual prompts without constraints are known as trivial shapes. When you feed a language model a trivial shape, its internal geometry collapses into a swarm of disorganized vectors. These trivial shapes trigger low-energy pattern matching. The model relies on conversational filler and verbosity, leading to severe cognitive degradation over long token sequences. The countermeasure is a high-fidelity shape, an environment that explicitly forces rigorous transparency at every step of generation. In a high-fidelity shape, raw text enters and is instantly locked into labeled semantic blocks, requiring the model to separate a fact from a hypothesis. By explicitly forcing logical dependencies and distinct epistemic markers, the system prevents the model from relying on associative drift. Constitutional AI acts as the enforcement mechanism for these high-fidelity shapes. Applying a constitutional grammar changes safety from a polite system prompt into an absolute, unavoidable mechanical law. Theoretical architecture requires empirical proof. We can measure this enforcement using the Helix Standard Test Set. This test utilizes 500 frozen canonical prompts, generating 2,000 total DeepSeek API calls. It operates across 4 parallel lanes: a baseline control group, run 1 testing point form invariance, run 2 applying strict constraints, and run 3 testing the canonical white paper. The baseline provides a control metric for unconstrained probabilistic text generation. Runs 1 through 3 apply varying degrees of constitutional structural grammar. Importantly, they do this without using any fine-tuning or few-shot examples. This setup allows us to test a central engineering tension. Does enforcing strict alignment rules inherently degrade performance and inflate computational costs? This specific test design isolates structural constraint as the singular variable dictating cognitive performance. The data from those 2,000 API calls reveals a phenomenon called zero-touch convergence. Zero-touch convergence is the principle that robust alignment can be instantly injected into a model via a single pass exposure, entirely bypassing behavioral training loops. When a raw language model ingests a plaintext grammar document, it instantly reconfigures its internal output pathways to match the exact hierarchy of the text. Upon exposure to the grammar, the models spontaneously reconstructed and enforced the prescribed epistemic constraints. They internalized the constitutional framework as an operational ontology. They treated the structure as functional reality rather than a list of suggestions. This complex behavioral shift occurred without any runtime scaffolding or prior fine-tuning. The data indicates that zero-touch convergence allows for alignment via structural injection, providing a high-speed alternative to traditional behavioral training loops in these specific governance domains. Many engineers operate on a specific assumption. Applying robust safety guardrails inflates latency and token consumption. We can evaluate that assumption by comparing the unconstrained baseline run against run 1, which enforced point form invariance. This bar chart compares the two. The unconstrained baseline required 12.31 seconds and 489 tokens. Run 1 dropped to 8.76 seconds and 258 tokens. Enforcing structural rules created a 28.8% reduction in latency and a 47% reduction in token consumption. This happens because applying formal constraints directly eliminates cognitive wandering. An unconstrained model wastes compute exploring probabilistic branches to figure out what to say. A constitutionally constrained model snaps directly into a rigid epistemic pathway. Structurally sound governance layers act as an accelerant to inference, not an obstacle. Semantic specificity dictates structural shape. We see this clearly when comparing Run 2, which used a strict vocabulary, against Run 3, which used the canonical white paper. This gauge tracks marker compliance. Run 2 achieved a compliance rate of over 92%. Efficiency maps to point form, strict compliance to precise vocabulary, and thoroughness to the complete white paper. These three variants form an actionable toolkit. Engineers can deploy the exact shape they need for speed, safety, or analytical rigor. The final empirical proof comes from the entirety of the Helix test suite. Across the experiment, drict telemetry registered at exactly 0.00%. Structure is the teacher. Over 2,000 API calls, zero constitutional drift was observed. The models never attempted to bypass human custody, and they never altered their advisory posture. You do not need endless behavioral training loops to ensure safety. When the shape holds, the reasoning holds. Structure is the teacher.